This morning's speaker is Professor Geordie Williamson. Geordie was born in Bowral in Australia, which means that despite his glittering career, the Australians and New Zealanders will know he will never be the most famous person to come out of Bowral, but very close. He did his undergraduate at the University of Sydney and then his PhD at the Albert Ludwigs Universität Freiburg. And then he had stints at Oxford and at the Max Planck Institute for Mathematics before moving to Sydney to take up his current position. He's a giant of modern geometric representation theory. He's done, I think, amazing and visionary work on using artificial intelligence and neural networks in trying to understand mathematics. And I also think we should just mention the enormous contribution that he's made to Australian mathematics through the creation of the Sydney Mathematics Research Institute, which is an amazing contribution to the landscape of mathematics in the country. So without further ado, I would like to introduce Geordie.
So thank you very much, and thank you also to the organisers for this chance to speak here, and thank you for your amazing efforts organising this wonderful conference. So I'm talking about neural networks and AI as a tool for the mathematician. I want to, however, start with a recent theorem of Tietus. Okay. So this is a beautiful theorem, and of course we have probably no idea who it's actually due to. So there's 5 regular solids. So this is discussed in the work of Plato. And I really love this theorem also as an example of what I think is a very beautiful theorem in mathematics. So there's a very clean statement, and then we have a classification. But I want to point out that if you don't know about the existence of the icosahedron or the dodecahedron, it's kind of difficult to imagine what the statement of this theorem would look like. So is an example of this interplay between, of course this theorem needs a proof, and a proof is famously given in the Euclid's Elements, which was kind of standard geometry textbook for about 2 millennia. But in order to try to prove this theorem, you need to know the statement, and in order to know the statement, you need to know the existence of certain objects it's maybe not obvious that these things exist. So one thing that I find fascinating here is that it's very unclear whether the people that first conceived of the icosahedron actually had a physical icosahedron. Okay? It doesn't seem to be present in Greece or Italy physically, and it's unclear if there was a model. So this might be one of the first objects in mathematics that was conceived of in the brain, which I think is very interesting to think about. And also, so those pictures are from Kepler, and you probably know this extraordinary story where Kepler was convinced that at that point there were 5 known planets, and Kepler was convinced that the ratios of the distances of these planets to the sun could be explained by the 5 Platonic solids. And then somehow his own intellectual honesty forced him to realize that this was not true and to discover Kepler's laws, which then, of course, were extremely influential on Newton. And so this has had an enormous effect on mathematics and physics, this theorem. And also today, in the Langlands program, there's icosahedral Galois representations, which are a major challenge. The icosahedron is behind Poincaré's disproof of a naive form of the Poincaré conjecture. So, we still see the icosahedron as a fundamental object in mathematics. Okay. So, I'm talking about neural nets for discovery, but if I talk about AI, then people think I'm going to talk about something else, so I need to have a slide that says I'm not talking about the following. So I'm not talking about AI in applied mathematics, even though this is absolutely enormous. So the effect of AI in applied mathematics is much, much more significant so far than its effect in pure mathematics. And also, so there's been a lot of work on formal proof. So formal proof assistance. So, Euclid's Elements, for example, contains gaps. He makes steps which do not follow from the axioms. And if you're worried that you might be doing that, you might use a formal proof assistant to check that your proof actually follows from the axioms. Okay? So there's been a lot of work in this direction. However, if you have a lemma and you don't have a proof, this is a major challenge. So give a lemma, maybe a lemma that's not so complicated to one of these proof assistants. Typically, it won't be solvable by current methods. And if you look historically, I think the progress of automated proof assistance has been extraordinary, but it's kind of striking how limited the progress has been made on automated proof. However, that seems to be changing at the moment. So alpha proof is a system which in July solved I think 4 out of 6 of the IMO problems, or at least it got a silver medal on IMO problems, which is very striking. So this is a DeepMind system from DeepMind. And I think it's realistic that within 1 to 2 years, there are systems which can prove kind of graduate level lemmas in Lean. Okay? And I think that it's important when you're thinking about this stuff, because often I think about, like, I choose problem X and I put it into, I don't know, the latest system from OpenAI or something, and I look, oh great, it can't solve it yet. Okay? But I think it's really important to look at the trajectory of these systems and to realize that I think that the fact that these systems will exist in the near future is kind of beyond reasonable doubt at the moment. There might be some very unexpected obstruction, so the statement might be false, but I think that if you had to bet, you would bet that in 1 to 2 years there's some system that can prove graduate level lemmas. But the other thing that is definitely possible is that such a system exists in 1 to 2 years, but we don't have access to it. And then there'll be another 1 or 2 years when people try to replicate this. Like, this is what happened with AlphaGo, for example. The first system was not publicly available, but then other people, there was enough information in the Nature paper to reproduce it. So this is what this talk is not about. Okay? So to come back to the first, the theorem on the classification of the Platonic solids, if we have the statement, then this slide is about proving the statement. But I think there's also a fascinating aspect of this story, which is discovery. Okay? Like, how would one find the icosahedron if one didn't know about its existence? So this is a quote from Gil Kalai that I absolutely love. So the methods for coming up with useful examples in mathematics are even less clear than the methods for proving mathematical statements. Okay? It's a very influential quote for me. Okay, so this talk, I want to discuss 3 hard problems in mathematics from different areas. I want to remind you, or give you a very brief introduction to what a neural network is and what transformers are. And then I want to explain how we've used neural networks on these problems. Okay? I want to emphasize that this talk is not meant to be contribution to neural network hype. Okay? I do think that neural networks are amazing things. I do think that one should try to use them. But I don't think that they can solve any problem. And I think that this talk illustrates that they're helpful on some problems, but they're certainly not a silver bullet. So they're part of an arsenal of techniques that we have at our disposal, and I find them very interesting, but I'm not trying to convince everyone to go and run off and just do neural networks all day. Okay, so now I'm presenting 3 problems. So this is a very difficult problem. So this is the Hersch conjecture from 1957. So I take a polytope. So you can think about this as something cut out by finitely many inequalities. So some bounded region of space cut out by finitely many inequalities. So it has an ambient dimension D and a number of facets n. Okay? And the Hersch conjecture says that if I take the vertex edge graph of this polytope, so the vertices of my graph are the vertices of my polytope, and the edges are the 1 simplices of my polytope, then that graph should have diameter bounded by n minus d. Okay, so here's an example. So I have the convex hull of 6 points in R2. So this has 6, it's determined by 6 inequalities. The dimension is 2. I can get between any 2 points in 3 steps, so its diameter is 3, and 3 is indeed less than 4, which is 6 minus 2 in this case. Okay. Another example is the cube. So this is a 3-dimensional cube, so the dimension is 3. It's determined by 6 inequalities, and I can get through between any 2 vertices in 3 steps. And so here I see 3 is less than or equal to 6 minus 3, which is correct. And the cube in any dimension shows that this inequality is strict. So, sorry, is whatever you call it. Yeah. Okay, so why do we care about this? So how hard is linear programming? So linear programming, I start with the polytope given by inequalities, and then I find a vertex, and then I start moving along edges to try to optimize some objective function. Okay? So this is an incredibly powerful algorithm. So, you know, maybe we've used it 1 billion times today or something. It's one of the most successful algorithms of the 20th century. But we don't know what its worst case running time is. Okay? We don't know how hard this algorithm is that we use every single day of our lives. Okay? So if you had a polytope of exponential width, in other words, that this diameter is growing exponentially in, let's say, n minus d, then the simplex method would be worst case exponential time. So there'd be certain linear programming problems that are much, much harder to solve than the generic problems that we see every day. Okay, which I think would be a fascinating possibility. And, you know, I'm kind of a contrarian, so I believe that these extremely unusual problems exist. And this is motivated by this extraordinary theorem of Santos in an Annals paper from 2013, where he says that there's a 43-dimensional polytope with 83 facets that breaks this Hirsch conjecture by 1. It's kind of amazing. And this work is very, very interesting. So the Hirsch conjecture is false, and we don't know how false it is. So if the Hirsch conjecture is true, then there would be no kind of combinatorial obstruction to linear programming being linear time. But as it stands, we don't know. So Santos has this extraordinary argument that reduces this problem to some 5-dimensional question. And, you know, since Santos's work, there's very few examples known. Very few examples beyond what Santos constructed. So there's probably like 3 more plus 2 interesting families or something, which required an enormous amount of work. And we've recently introduced this. So this is with researchers at DeepMind. So there's this Hopper algorithm that produces millions of counterexamples, as well as the smallest known counterexample. Okay? So I'll discuss this later. So this is the first problem. The second problem, so this is belongs to extremal combinatorics. So what is the largest blah satisfying blah? Okay, so what is the largest subset of an n by n grid without isosceles triangles? Okay? So here I'm building up, so I have a mathematician's Go board, and I add black stones, and I'm allowed to add a stone as long as I don't create an isosceles triangle. Okay? And this is somehow a very interesting problem because it's very non-local. Like, you know, when I add a stone down in the bottom left, I might create some very long isosceles triangle. And I'm kind of cheating here, so this is actually the best solution for a 16 by 16 grid. So I was very clever in the way that I placed my stones. If you just tried to do this randomly, you wouldn't get anywhere near this construction. So, you know, what I'm saying is that this construction has no isosceles triangle, so that blue triangle is in particular not an isosceles triangle, and also it's maximal, so no matter where I add a point, I create an isosceles triangle. I think if you look at this, you know, the first time I saw this, I'm like, surely I can find another point somewhere. But you can't. Okay? And you also notice this kind of beautiful, like, we didn't impose symmetry, but there's an emergent symmetry in this maximal solution, which is rather nice. Okay, so there's this very famous progression-free subset of the integers problem, which is related, for example, to the Green-Tau theorem on progressions in primes. And this is a 2D variant of that progression-free subsets problem. So little is known about optimal solutions in this 2-dimensional case. And it's even, so this is kind of very close to combinatorial optimization in computer science, and in many problems in combinatorial optimization, you don't even know how to get like even close to the optimal solution. You know, you'd like to get a reasonable solution, and even that's very hard. Like on a 1,000 by 1,000 grid, we have absolutely no idea what to expect. Okay? So, you know, on a 16 by 16 grid, one can use, you know, SAT solvers or something like that to get an exact solution. But I'm interested in the question, like on a 1,000 by 1,000 grid, what's a decent solution? Yeah, so this is also highly addictive. Okay, so this is the third problem. Does the Jones polynomial detect that unknot? So of course Jones hails from New Zealand. So we associate, so very famously to a knot we can associate a polynomial. And so here I have a very complicated knot and I associate a completely made up value of the Jones polynomial. I didn't actually work this out. And you can ask yourself, so it depends on your normalization, but in my normalization, the unknot goes to the polynomial q plus q inverse. And now you can ask, imagine that I have some very complicated knot, and it goes to q plus q inverse. Is it the unknot? And we don't know. Okay? It's a very fascinating open problem. And you can phrase this, so many people have thought about this problem from many different points of view. And one formulation of this problem that I find attractive is this kind of matrix problem. So you consider these two innocent-looking 3x3 matrices. And we want to know, so we take A, B, A inverse, and B inverse, and we ask them, do they satisfy any relation? And we don't know. Okay. So this problem was famously raised by Berman in 1974. So I'm asking, you know, do these two matrices generate a free group? And if they don't, then the Jones polynomial does not detect the unknot. And I'm giving this as a kind of example of the type of problem that we're considering, and when I'll state results later, we're actually studying, we're actually discussing the faithfulness of certain Jones representations for the experts. Okay? So there's the problems. So now I want to give a lightning introduction to neural networks. So I hope you've all seen line of best fit. Okay, so here's a line of best fit. So I just want to imagine this is a rod and it's getting pulled by certain bits of rubber and fits into my data. So there's the convex optimization problem, unique solution. No matter how I do this, I always get the same answer. So we're very happy. And then I think the simplest way to think about a neural network is as a kind of nonlinear regressor. Okay? So here I imagine instead of having a rigid rod, I imagine a rod that's somewhat bendable. And then as so the data will pull the rod in a certain way, in a kind of linear way, but then it'll start to bend. So this is like this is really an example of training a neural network on this particular data set. Okay? And you'll notice that it first picks up the kind of main bends in the data, and then it starts to bend more. Okay? So I think it's, you know, and I should say it's really just a very first approximation of what a neural network is. So, you know, in the 80s and 90s and noughties, people were saying, you know, neural nets are just nonlinear regressors. What's all the fuss about? And they really appear to be doing more, but if you want a first mental picture, this is what one should have in mind. So this is the kind of actual setup. So we have, basically we have a big class of functions, that's all possible rod positions or something, parameterized by a whole lot of linear or affine linear maps. And then we have a loss function which is related to our data. So this is like the kind of force exerted on our line or our surface or our high-dimensional thing. And then, you know, as we train via some variant of gradient descent. And this, we get a good approximation, hopefully, of some function. Okay. So transformers are a type of neural net architecture which are really revolutionizing lots of areas of AI. So they were introduced in 2017. And I'm not going to go into the details, but they're, you know, what, for example, large language models use. And their initial goal was translation. But I just want to point out that transformers can be used in any case in which you have some kind of sequential tokenized input. It doesn't need to be language or something like that. That's very important. So this is typically what a transformer would spit out, is that we have some token sequence, like nobody expects, say, and then the transformer will give us a probability distribution on the next token. So I just want to state that more precisely because I think it's important. So we have some sequences of tokens which come from some distribution. So for example, language, but potentially DNA sequences or something like that. And we just want to predict the conditional probability. So given that my first m-1 tokens are t1 up to tm-1, what's the probability of t? And this is, it looks like an innocent looking function, but this is extremely difficult to compute. This function is very, very difficult to compute, for example, in language, and transformers provide a way of computing these probabilities. Okay, so if we have f, so we have a trained transformer, we can now sample or generate like fake things from this distribution. So we put in the empty sequence and we get a distribution over tokens, and then we sample. And then we say, okay, I've taken this one. Now, what's the distribution on the next token? And then you sample and you say, okay, I've taken T1 and T2, etc. Okay? And so this is what is happening when you're using large language models. There's this many-stepped sampling. Okay? So just some philosophy about transformers, which I find attractive. So I find this like a very useful way just to think about what transformers are doing, even if you know almost nothing about transformers. So there's good old-fashioned AI called GoFi. Okay? And this is a very interesting subject, and this was subject of a lot of work, for example, in the 80s and 90s. And there the idea is that when we're doing symbolic manipulation in the brain, we're literally manipulating symbols in our brain. Okay? So this would say, for example, that the language that you speak fundamentally influences the way that you think. Yeah, so it really influences the tokens that you're using. Yeah? So that's the GoFi hypothesis. And then there's recurrent neural networks, RNNs, which say that there's just one representation. So this is representation in the sense of machine learning. So if I'm reading Anna Karenina, I have a particular state in my brain, and then every new word is just updating that state conditioned on the word that I read. Okay. And transformers, I think it's fascinating to think about them as a mix of the two. So it's not symbols, but also it's not just one representation either. There's some kind of representation of tokens, and then these tokens are speaking to each other in some way. Okay? So there's a really interesting interview with Jeff Hinton at the Sana AI Summit where he explains this point of view, which I think is very worthwhile to listen to. So, applications in mathematics. So, before I go into this, I just want to tell a story. So, when I was 8 or something, I was annoying. And my brother was also annoying. And so my mother dealt with this by asking us, when we were being particularly annoying, she'd say, go and find a 4-leaf clover. Okay? And so we lived on this big farm, and so my brother and I loved finding 4-leaf clover. And so we'd run out and we'd search for hours, and we'd finally find one, and we'd run back and we'd be like, Mum, we found one. And then Mum would be like, good on you. Okay? And then, so we did this many times, but then something funny happened, which is that we found this particular patch that had a very high number of 4-leaf clover. Okay? So we still needed to search, but now the search was like 10 minutes or something. So Mum would say, go and find a 4-leaf clover. We'd be like, yep. And so she had to then change strategy. Okay? And this is really a metaphor for using neural networks in search. Okay? So if we're looking for examples, we don't just do brute force search as mathematicians. We have some idea of what the solution is likely to look like, even if it's very vague. And typically neural nets are very vague. They're very kind of heuristic type things. So computers are very good at searching, but you just can't ask them to search over a set of size 10 to the 50 or something. But if you ask them to search over a set of size 10 to the 10 or something, you're probably going to be fine. Okay? So, you know, in all of this, there's still a lot of search involved, but we're using neural nets to narrow the search a little bit. Okay? So that's a very important principle. So, you know, an interesting example of this. So, you know, I was talking to DeepMind about the alpha proof thing, and then one of their people, so they have a kind of sampler. So they have a sampler and a checker. And on one of the IMO problems, they had someone look at like 2,000 possible solutions coming out of the system. And most of them are very bad, but, you know, 2 of them were correct. And, you know, if you have computers, then finding 2 correct you're already very happy. Yeah? So we're just after a little bit of help from neural networks. We're not asking for neural networks to kind of completely solve the problem. So this is the first technique which I'm probably the most excited about. So this is learning from good but not great solutions. So we apply this technique in this isosceles-free example. So the first thing that you would think about if you're programming a computer is just to do a random local search. So you place a stone, place another stone, check that it doesn't create an isosceles triangle. If it does, then you add that to your list of points where you shouldn't try to add a stone in future, and then you try and add it somewhere else. And then you keep going until the points where you shouldn't add a stone are all available options. Okay, so that means that there's no way that you're now at a local maximum. There's no way to add any more stones. Yeah? And if you do this, you'll get something like what is pictured. Okay, so again, it looks like I could add another stone to create a better construction, but in fact I cannot. Okay? And these solutions are typically very bad. Like, they're very, very far away from the best solutions. Okay? But maybe there's some interesting, I don't know, I don't want to say insight, but like, there's something interesting in the top 10% of these solutions. Okay? So just a stupid example of this is like, you know, I'm sure you're all familiar with monkeys on typewriters typing sonnets. Yeah? So the chance of a monkey generating a sonnet is 10 to the minus 53 or something like that. But if you could somehow train the monkey to produce words or produce things in sonnet form, then suddenly the probability of generating a good sonnet is down to like 10 to the minus 10 or something. Yeah? So what we view these, so we generate a whole lot of constructions by local search, we take the top 10%, and we regard these as sequences of tokens. So it's a little bit more complicated than that, but you can just think that we just tokenize it as 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, or something like that. So this is just this is a word in a language. Sorry, it's a sequence of tokens. So that's one example of something we'd like to imitate, and then we train a transformer. Okay? So this is a very kind of out-of-the-box thing that you can download an implementation of a transformer. And now you sample from the transformer to produce new examples. And so the hope is that the transformer is picked up on some patterns in these reasonable constructions, and that it's going to, with greater probability, reproduce those good patterns. Okay? And remarkably, this works. So most of the samples are bad, but some of them, if you try to fix them up, now suddenly you can add more points and you get better constructions. Okay, so here's a picture of the kind of distributions before and after this process. So on the left, you have something like this. And then once you've gone through this business of training the transformer and you sample, you see kind of some residue of the old distribution, but then you see these kind of very interesting good constructions. Okay? And now you can iterate this, and this is extremely interesting. So, you know, typically we can iterate this loop about, I don't know, between 20 and 50 times before you get a kind of collapse of the model. And this is also interesting because, in transformers, if you kind of train them on their own output, they degenerate very quickly. But what we're doing is we're not quite training on their own output. We're taking their output and then seeing if we can fix them in some way. And so we're disturbing the distribution a little bit and then retraining, and this seems to be enough to stop model collapse. Okay. So this works surprisingly well, in some sense, out of the box on several problems. So this example on the right I really love. So Adam Wagner is very, very obsessed with this isosceles free problem. And he had spent many months using kind of classical search techniques to generate the best solutions he could for the 64 by 64 grid. And we suspect that the best construction is 112, and he was able to find 104. And after many, many months, he was able to find like about 50,000 constructions with 104 stones. And then he put this in, so then he put this into the transformer, sampled from the transformer, and immediately found a 108. Okay? And now we've found several 108s, and we still haven't found the mythical 112, but it's clear that the transformer is doing something, and it's like a very interesting additional component to some kind of local search. So we also found a counterexample to a very innocent sounding 30-year-old conjecture of Graham. So what's the smallest subgraph of the graph of the hypercube, which still has diameter n? Okay. So if you think about this for a minute or so, there's a very kind of natural construction, and Graham conjectured that this construction is the best possible. And this appears to be the best possible up to n equals 5, but this loop found a construction with 81 edges versus the conjectured 82. So I just want to emphasize that this technique is really, like I'll talk about, in the next section, I'll talk about like a very kind of sophisticated system that required a lot of engineering, but this system, I can run on my laptop in small examples, and I can, with one GPU, I can do all the experiments in this paper, basically. So it's reasonably standard tools, and it seems like this could have applications outside of mathematics, and we call this loop pattern boost. So you kind of, this loop of local search together with transformer. Okay. So now I will move on to polytopes. So this is the Hausch conjecture, and so we would like to have a system discover counterexamples to the Hausch conjecture. And how does one generate interesting examples of polytopes? So I should emphasize that in this particular problem, none of the researchers had any background in polytope theory. Okay? So we're just starting incredibly naively. And I think that's also important in these things, that like we're obviously not giving expert knowledge because we're not experts. What's the most naive way of building up a polytope? It's by, adding vertex by vertex at a time. Okay, so this is what we do. But the question is, like, where do you add a new point? And now I'm drawing a 2D picture. So between any 2 points that I've added so far, I can draw a line. And then this cuts up space into different regions. And it's extremely important that I don't add points just kind of randomly in space. Basically because the combinatorial type of the polytope that I get by adding a new point depends only on that region, and sometimes these regions can be tiny little chunks of space. And so if we just place points randomly, there's no chance that we'll put a point in this tiny region, but we should not forget about that region. Okay? So somehow one needs to keep in mind these regions, and it's like from the point of view of a kind of one-player game, if you think in terms of these regions, it's just absolutely bonkers, because you add a couple of points and then you ask, how many regions do I have to add? And you've easily got 1,000 and then 1,000,000, and then, like this is a realistic example in our search. So if you have 20 points in 4 dimensions, then there's like 22 times 10 to the 12 possible moves. So if you went to Percy's talk, we're talking in solitaire, there's probably 5 possible moves or something like that. And now we've got some insane number of moves, and they're parameterized in a very difficult way. Okay, so the basic idea is to not care about the regions, but care about the hyperplanes. So we try to guess which hyperplane will be involved in a region that will produce an interesting move. So we start by randomly generating polytopes, and then we have various heuristics of like, is this polytope interesting? And then we try to remember which hyperplanes were involved in interesting moves. Okay? We then train a neural network to predict which hyperplanes will be involved in good moves. And then after many months of cycling and training and things, you get a situation in which 1 in a billion searches is yielding a counterexample. Okay? So it's still definitely not producing a counterexample every time, but it's in the realm where one can just like let this system run and produce many, many counterexamples. Okay, so we get millions of new counterexamples to the hash conjecture. So, and we've checked that they're all like different. And one thing that's very annoying about this, which is partly one of the annoyances of collaborating with industry where you can't actually see everything that they're doing, is that the transformer appears to be doing something, but this is difficult to quantify. So researchers at DeepMind tell me the transformer is definitely doing something, but if I ask them, like, can you show me the evidence? They're like, well, I stared at this plot that I don't understand it. So the thing that I find most interesting about this is that we have a system that's somehow very agnostic to any. There's no kind of priors in terms of what polytopes we're looking for, but it seems to converge on polytopes with a very kind of striking geometric structure. Okay? So I find that very interesting because it kind of tells us where one may look if one wants to understand this problem further. Okay. Okay, so now I just want to finish up with the Jones polynomial. Does the Jones polynomial detect the unknot? So again, we focus. So I should say this is like a big project with lots of, it's basically a computational project and there's very little AI in it. But we did an AI experiment in the middle of it, which I find extremely interesting. And I want to finish with this experiment. So we're focusing on these kind of problems. Not exactly this problem, but these kind of problems. So we have a bunch of matrices. Do they satisfy some unexpected relations? Okay. And can we find these unexpected relations? And there's been a lot of work on this. And so in particular, the work of Bigelow produces a way of constructing interesting relations in many cases. And we're able to reproduce his results as well as find many, many more relations. And it's interesting because Bigelow's approach uses a lot of like very beautiful understanding of the problem. And our approach is very raw. It just uses the matrices. Okay, and we're not able to find any previously unknown cases of non-faithfulness. So, it'd be great to be able to say that we found a knot with trivial Jones polynomial, but we cannot. So I just want to focus on a small part of this, which is this use of neural network. So here's a thought experiment to motivate this. So your task is to find a particularly rare flower in the bush. So you've been searching for like days and you haven't found anything. And there's kind of two options here. You can say, okay, I didn't find anything, I give up. Or you might say, I've learned something, but it's kind of unclear what you've learned. Yeah? I've learned a lot about the bush. Yeah? I haven't found the flower, but I've learned a lot about the bush. Okay? Can that knowledge about the bush be useful in some way? Okay? And I think that it's kind of intuitive that the answer is yes. Yeah? So if you're now, imagine you have a bit of a break and then you're going out and you're searching again. And now you might think, okay, areas that look unexpected to me are more likely to have this rare flower that I'm looking for. So the areas of the bush that are totally predictable for me I probably should ignore, and I should concentrate my search on areas which are unpredictable. And I think that we would intuitively do this. Okay? So if you want to concentrate your search on areas of maximum surprise, so you want to look in areas where you're surprised the most. Okay? So we're looking for a rare knot or a braid. So we're looking for a rare knot, but braids can be turned into knots by closing them up. And so actually we're looking for a rare braid. And what we do is we train a neural network to predict an important property of the braid, which is kind of loosely related to the actual thing that we're looking for. Okay? So this is like our predictive capacity in our environment. This is So the neural network achieves very good accuracy on this problem. And so maybe you can think about this like predictor as kind of filter. So if it's able to predict well, this is probably boring. But if it's able to predict poorly, this might be interesting. Okay? So we introduce like a descent set confusion. So this is the difference between our prediction and the reality. So this is like, in some sense, how surprised our neural network is by this particular braid. So now we pursue braids with high descent set confusion. So we spent some time implementing this, and it's just amazing that it actually works, I think. So this is depiction without the neural network. So this is our search, and basically we want lines that come back down. So this is a whole lot of different searches. So we're going off into the bush, and then if we get back down, so there's a few there that drop back down, and they're our successful searches. Okay? And then the ones that don't drop back down are the unsuccessful searches. And then this is when we introduce the descent set confusion in the neural network. So suddenly, we find many, many more interesting relations. Okay. So I think this is a very interesting idea for kind of future work with AI and mathematics, to kind of train neural networks generally with predictive capacity, and then to look where they're confused. Yeah. So just to summarize what I've said, I've presented 3 examples where we find some new things, but the results are mixed. On no problem do we find a complete solution, and each of the applications are somewhat distinct and different and interesting. And so, I think it's very difficult a priori to say how helpful a neural network would be on problem X. So, we're at the beginning of a field. And we're just exploring, and we're seeing what works, seeing what doesn't, trying to get intuition. But at the moment, our intuition for what works and what doesn't is very limited. Yeah? So you just have to try stuff. And I think we're seeing some very interesting things. And these techniques are very flexible, and so I imagine once we have a picture of where these techniques might work, it seems like there's just an enormous possibility for neural networks in this kind of explorative mathematics direction. So thank you very much.
I'll just remind you, when you ask your question, if you don't want to ask it twice, wait for the microphone to come to you. So, Ollie?
Thanks for a great talk, Geordie. I was very curious about your 112. Of course, it's maybe not the experimental bit. Where did that number come from? Was it 112? When you're
yes, so that was, so we used the SAT solver to get the optimum solutions to about 35 by 35, or in that order of magnitude. And there's a very clear linear growth there. So, so I think one doesn't know. Yeah, we're interested in this problem because you have no idea, like, is it root n, or so it's very different to the arithmetic progressions in that respect. So one has no idea where it sits, and the SAT solve is really indicated that it's linear, and then one can fit like, pretty precise line to that. And then that's what our 112 prediction is based on. Yeah.
So I think Jan also had a question.
Yeah, thanks, Geordie. Great talk. So are you able to comment on the type of problems that you could do with a simple MLP and where transformers are particularly relevant? It's like more like where attention is important or not?
Yes. So, yeah, just to repeat the question. So we have MLPs, which are the very kind of vanilla neural network architecture that I introduced at the beginning, and then there's transformers, which are more adapted to kind of symbolic inputs. And yeah, I would say that, I mean, my core belief is that transformers will be, we will be using transformers all the time in the future. That they're really like a very fundamental kind of new architecture that contributes something like very significant beyond what an MLP does. And yeah, and also MLPs you can see as kind of baby transformers if you want. So yeah, I guess just very, very roughly, if you have some kind of vector, vectors in, vectors out, I'd probably try to use a MLP. And if you have some kind of symbolic input, I'd try to use a transformer. But also I feel like trying to incorporate transformer thinking on typically MLP problems is useful. So, if you have the time, I would say always try to use a transformer.
So given that you, over here, other side.
It's just a voice coming out of the, where is this voice? Oh yeah, g'day. Yeah.
So given that you've, say like 1 to 4 years, you think this AI is going to be much more widespread, do you think, say like as an ECR researcher, like now's the time to get ahead of the curve, start trying to familiarize yourself with that, or like keep working on the theoretical, I'm going to say maths non-AI side, and then sort of be ready, knowing it's coming? Like, what would be your advice?
Okay. So I'll give my honest opinion, okay? And this is just my opinion, so treat it with a grain of salt. There will be enormous demand for work in AI safety, reliability, and alignment in the future. And mathematicians can contribute to this significantly. And I think that it's important that some proportion of mathematicians try to use these techniques. But I think at the current level of pure mathematicians working with neural networks is maybe like, I don't know, 1% of mathematicians or smaller than that. And I feel like that number could be a little bit larger, but I feel like that order of magnitude is good for mathematicians using neural networks on maths problems. But yeah, I think this direction of alignment is like fundamental and important, and will grow greatly in the next years.
Did you try baking symmetry requirements into the initial icosahedron problem, or why did that not work?
Yeah, so one thing that I haven't discussed is all of the technical questions that one has to confront when using neural networks. And one of them is, should one try to have symmetry as a prior or not in the search? Like, in this isosceles free example, you might just hypothesize that the maxima are symmetric and then drastically decrease your search space. And we did actually, in that 64 by 64 example, their symmetry is included. And in our pattern boost paper, we do study situations in which we bake symmetry in and not, and that's one of the many things where I have no intuition. Like sometimes it helps, sometimes it doesn't, and you've just got to try.
So yeah, thanks for your talk. I particularly enjoyed your comment that you're trying to figure out what this computer is actually doing. And that made me wonder, so if you're taking the analogy of going in the bush and you're learning nothing from your rare flower because you don't find it, but you learn all these other things, then you are observing something and you are making deductions of what is not an interesting area. And so what you put in the computer is your observation of what is not interesting. so that the computer can then maybe figure out what the interesting regions are. So are you in some sense understanding your brain on how you think and that's what you put in the computer? Or do you think the computer is actually figuring out something new?
Yeah, I think that's a really interesting question. I think that there's like in some sense, the sense set confusion business is motivated by this idea of like predictive coding and things like that in neuroscience, that we're perceiving very little of the world and we're predicting a lot. Yeah? And there's a lot of attempts to, and if you think about generative models, I think they're very interesting, like there's very interesting connections with predictive coding. And I think that this, like predicting what you expect from your environment, so in the example of braids, we're really hard coding a particular thing and saying, try to predict that. And I view this as a baby step towards much more general predictions, and that then guiding search. But you know, this is just something that we did in a week to have fun. And yeah, I think this, like, I think that we're very much guided by surprise as mathematicians, and I think that's fascinating. Like the example that doesn't quite fit our mental model of the world is the example that then leads us to cultivate new intuition.
Yeah, but you're defining surprise to the computer, right?
Yes, we are defining surprise, and also I think that there's like good evidence that our objective function in the world is like minimizing surprise. So if there's something baked into us as cognitive beings, it's minimizing surprise.
Yeah, so who's the next person to find an icosahedron? Is it a computer?
Well, let's see.
All right, so we may have to leave it there so we can enjoy our morning tea. But thanks, Geordie, again for
Enjoyed your talk very much. I'm Scott. We met at ICM down under in 2022.
Oh, no.
I had a question actually.